Now I want to talk about local maximums and minimums when I'm working with two or more variables. When I have maximums and minimums in R3 space, my surfaces are far more intricately detailed than a simple line in R2 space. But I can still examine a surface for places where the surface climbs to a peak, which is a maximum, or descends into a hollow, which is a minimum. Now, between these two extremes can lie all kinds of other features, such as extended ridge lines, valleys, or saddles. Even though curves and surfaces have significant differences, we can still extend all of the work we've done so far regarding local extrema for functions of one variable to functions of two or even more variables. We're going to use the same convention that we used before, that local maxima and local minima will still occur at points that are on the interior of the domain of my function. The local maximum value of a function f at the point AB occurs when f of xy is less than or equal to f of AB for all xy in the domain of f in some open disk that's centered at the point AB. A function f will have a local minimum at the point AB if f of xy is greater than or equal to f of AB for all xy in the domain of f in some open disk centered at the point AB. The local maximum and local minimum values are also called the local extreme values or local extrema. So if f does have a local maximum or a local minimum value at the point AB, and the partial derivatives fx and fy exist at that point AB, then fx at the value AB should equal fy at the value AB, and they should both be equal to 0. In the case of a function of one variable, we know that if a local extrema exists at the point AB, then the line tangent to the curve at that point is horizontal. In a function of two variables, if a local extrema exists at the point AB, then the tangent plane at that point will be horizontal. Now, it's important to note that the presence of a horizontal tangent plane does not guarantee a local extrema at that point. It only gives us a possible candidate for local extrema or critical points. So we need to locate all the critical points and then be able to test whether or not it happens to coincide with a local extreme. An interior point AB in the domain of f is a critical point of f if one of two conditions exist. If fx at AB is equal to fy at AB and they are both identically equal to 0, or one or both of fx or fy does not exist at the point AB. Either of these conditions will give me a critical point of my function on the interior of the domain at the point AB. So let's work an example. I want to find all critical points for the function f of xy is equal to x cubed over 3 minus y cubed over 3 plus 3xy. Fx of xy is given by x squared plus 3y. Fy of xy is equal to negative y squared plus 3x. These two have to be equal to 0. This means that x squared plus 3y is 0, which gives me y is equal to negative x squared over 3, and it means that negative y squared plus 3x is 0, which means that x is equal to y squared over 3. If I look at my x equation, x is equal to y squared over 3, and substitute negative x squared over 3 for y, I get x is equal to the quantity negative x squared over 3 squared divided by 3, or x to the fourth over 27. This gives me 27x is equal to x to the fourth. This can be written as x times the quantity x cubed minus 27 is equal to 0. This gives me the possibility that x is 0 or x is 3 using only the real roots. Plugging x is equal to 0 into my y equation gives me y is equal to 0, and plugging x is equal to 3 into the y equation gives me y is equal to negative 3, so that my critical values are at 0, 0, and at 3, negative 3. Now you get to try it. Pause the video and find all critical points for the function f of xy is equal to x squared plus xy minus 2x minus y plus 1. When you are ready, restart the video to check your understanding. So I'm looking for all critical points for my function f of xy is equal to x squared plus xy minus 2x minus y plus 1. Fx at xy is given by 2x plus y minus 2. Fy at xy is given by x minus 1. I know that 2x plus y minus 2 has to equal x minus 1, and both of them have to equal 0. So that 2x plus y minus 2 has to equal 0, meaning y is equal to 2 minus 2x, and x minus 1 has to equal 0, so that x is equal to 1. If x is equal to 1, y is going to be equal to 0. There is only one critical value here, and that is at the point 1, 0. Be sure and let me know if you have any questions about finding critical values to help locate local extrema in my functions.